Good afternoon, everyone. So I'm just waiting for a couple of minutes to to have all the students here. I think there are um, a few students missing. All right. I guess I'm gonna start. It's already 2 minutes late. So, all right. So first, let me just introduce myself. I am an associate professor at the Electrical and Computer Engineering Department. So I teach usually electromagnetics and photonics related courses, and I do research on, especially in these days, about optical super resolution imaging, optical materials, quantum computing, and things like that, and also um, photonic materials, optical materials. These things are actually related to electromagnetics as well, and so what I'm gonna do today, I'm gonna start with the syllabus, and I'm gonna just briefly introduce the course. So in order to do that, I still keep getting new students. Okay, so I think there are still a few missing. So I'm gonna share my screen, and I'm gonna just show the syllabus. Okay. Guess it should be this one. Oh, no, not this one. Just give me a second. So it should be this one, I guess. All right, I guess you all see the syllabus. So this is the EE3140. And so let me just briefly introduce this course. So, and I already mentioned about these, but let me just, I have the office location and phone numbers here just in case, and hopefully things, resolve. And in that case, you can use this information here. But in the meantime, you can always send me an email, or you can make a Zoom appointment if you have any questions about this course or anything related to electromagnetics. Please feel free to send me an email or make an appointment. And then the
Beyond that,
grader
they had asked.
will be, the paperwork is still in progress, but Stefano Kesto should be your grader. He took this course before. So I think it will be a good, it will be good to have him as a grader here, and he will grade your homework assignments. So, oh, this should be updated. So this is a remote course. And what do we, what will we talk about in this course? So this course is a electromagnetism course for, it's kind of a, intermediate level exposure to electromagnetism. I'm assuming that, the students are familiar with the basic concepts from the physics course. So here we will look at in more detail into the Maxwell's equations, how the Maxwell's equations are solved for different electromagnetic problems. For example, to understand the operating principles of electromagnetic devices ranging from antennas to, to different kinds of, equipments that you may even see at your home, from like microwave oven to the large networks of antennas that are all related to the electromagnetic waves, how they propagate, how they are transmitted, how they are received by antennas, and And in order to understand how all these devices and systems work, it's important to understand the propagation of electromagnetic waves, and in fact, electromagnetic waves are basically governed by Maxwell's equations, as long as you're not dealing with quantum phenomena. So we will be looking at the essentially the Maxwell's equations, how this how the Maxwell's equations define the propagation and the behavior of those electromagnetic waves in different devices. And we will also look at from a mathematical point of view, we will basically look at the complex mathematical function of electromagnetic waves, because in general we represent electromagnetic waves as complex fields. And I'm going to actually start with that today, just very briefly introduce complex fields, because that's how we in general represent electromagnetic waves, in general. And we will look at the electrical properties of materials. This is essentially related to how electromagnetic waves interact with materials, because most of these devices, antennas or other devices which use electromagnetic principles, essentially interact with the material. Electromagnetic waves interact with the electrical properties or the magnetic properties of the materials, and that's how we build these devices, by controlling this interaction. Okay. And then we will look at the polarization and some simple electromagnetic devices which constitute the underlying components for more complex electromagnetic devices and systems. And these include essentially waveguides, resonators, transmission lines, antennas, and yeah, these are those building blocks. And then we will also, at the end of our lectures, I'm going to also introduce the optical waves. Optical waves is just another subset of electromagnetic waves, but typically optical waves are at very high frequencies, from terahertz frequencies to up to ultraviolet, and above even, you can see optical waves. They have, because the frequency is relatively high compared to microwaves or radio frequencies, the devices which we build also are actually they are much different than the microwave or low frequency devices. So there are some key differences between optical frequencies and the lower microwave or radio frequencies. So we will also see those differences, which impact the devices as well. All right, so these are the things that we will cover. And I already mentioned this, so I don't want to describe it more. So this is basically the same thing which I almost explained above. And then the course, this is the textbook that we will use. And then this is the grading scheme. So basically, we will have 3 exams, okay? And these exams, each of them will be equaluated 25% each. And then there will be homework assignments, which will be 25%. There will be 6 homework assignments. And it's almost, every other week, I'm going to assign a homework. And so you will be basically studying the material that we would be covering in our lectures. So that would be a good opportunity to master those concepts. And also what I'm gonna I just received a message about the book. So this book will be I mean, there are a lot of concerns about this book, but this book is sufficient to cover these concepts which we are talking about. Okay, there are a lot of examples, in the back of the chapter. You can you can use these, you can use that chapter to answer the questions. Even if I don't assign them, you can try to solve those problems, because those problems are really useful to understand the concept and to solidify the the understanding of these concepts. So there are basically, yeah, of course, you can always go to the webs, YouTube or other Wikipedia, and there are a lot of resources on the web. I don't have a specific recommendation about that, but I think it is sufficient. I mean, I think this, if you go through this lectures, attend regularly and do your homework properly, I think you should be in a good shape. You don't need extra resources, but of course, if you want to learn more, there are always a lot of resources. You can go to YouTube and learn more. For example, I may not be covering a specific topic in more detail because we have a limited time, but of course there are a lot of resources that you can find through Google, and especially in YouTube and Wikipedia. I can also point to you different resources at the time, when I'm not giving further detail. Okay, but if you really take this course, attend it properly, and take the exams and do the homeworks and everything properly, I think you should be in a very good shape, and you don't even need external resources. But if you have time, of course, it's always a good idea to learn more. Anyway, so now, and another thing which I want to say about the homework is that I'm going to assign the homeworks and then I will not distribute the solutions. However, what I'm going to do is I'm going to actually briefly show, I'm not going to solve the solutions, but solve the problems, but I'm going to actually show you briefly how to approach the problems, and how to basically, I'm going to tell you the method of solving these homework assignments. And I will do this usually before the midterms, and the midterm problems may be relevant or related to the homework assignments. So I therefore recommend you to pay close attention to homework assignments. Make sure that you understand it. There might be some differences in the midterm assignments. It will not be, of course, exactly the same homework problem, because otherwise it would duplicate it. But if you understand the homework assignments, if you do it yourself, and it's gonna be your midterms will be very, very simple, actually. So you won't really suffer about it. And it's gonna be, by the way, open book type of midterm. So it's gonna be open book, open notes. That's one thing which I want to mention. And this topic, or this course will include the chapters here, which is, again, related to my discussion a few minutes ago. So these are the topics which we will cover. Of course, if you have also more time, you can read the remaining chapters of the book as well. It's going to be really very useful. I, in fact, encourage you to do that whenever you have more time. Because in this one semester, we can only cover a specific number of chapters. And which are the most important chapters to begin with. So that's why we selected these chapters. And then this is just the schedule. So you can check the schedule here. So I guess that's pretty much what I have about the introduction of the course. So if you have any question at the moment about the course, let me know. So you can use the chat box, but I in fact encourage you to use just interrupt and speak. I think that would be easier, because otherwise I need to follow the chat box, and which may not be very convenient during the lecture. So so do you have any questions about the course?
Will you have office hours?
Oh, about the office hours, I don't have a specific office hours, but I encourage you to just send me a Zoom invite anytime you want. You can double check with me, of course, and then send me just a Zoom invite.
Okay.
Okay, or if it is a short question, or if you want to, just send an email, that's fine too. But if you want to, do it sort of in person, then you can just send a Zoom invite. I encourage you to do this. This is important. And in some cases, I may combine the Zoom invites in case there are questions from multiple people if it works. But regardless, you can just make an appointment by Zoom.
Are there any times that work better than others, or is it just kind of?
It's there is no really. I mean, I think you can just send me an email at the time. I mean, well, at the moment, I would suggest just before you make an appointment, just send, because my calendar changes week by week, unfortunately. So it's difficult to say. Oh yeah, you can do that. I mean, I think you should have access. If not, let me know. Yeah, that would be good. You can look at my calendar, and you can just propose a time. That would perfectly fine. Yeah, I think that would be the best. Mhm. All right. Any other question? All right. So if you don't have any other question, I'm gonna start with today's lecture. And the first thing which I'm gonna talk about is the complex vectors. Okay, so let me just stop sharing my screen. And there is one question about the book. Unfortunately, it's not integrated into Canvas. You need to buy the book. Unfortunately, that's the case. Yeah, let me see. Normally, the lectures, if you attend these lectures, regularly, you don't need the book. The only thing is that, when I assign the homework problems, some of the questions may be from the back of the chapter. I cannot actually, I haven't decided that yet, but in case I ask questions from the back of the chapter, you may need to have access to those questions. Otherwise, you don't actually really need the book, if you really attend these lectures. But it is a good resource. I think it's good to have it, just for general use later in the, related to electromagnetics. All right, so let me just share my other camera. And okay, so what I'm gonna do, actually, oh, by the way, I also want to mention that I'm gonna record these lectures. Okay, so this means you can go ahead and look at these videos when you want to review it if you want. But I still encourage you to take a note, because the thing is, if you don't take a note, it may be difficult to find what you're looking for. Unfortunately, video search is not that much advanced at the moment. So you can take a note like in the classroom. And because, as I said, I would be doing open book, open notes kind of exams, it would be useful to have these notes with you at that time. But it's, if you have the book, that's fine too. So I leave it to you, but this is just one thing that you may want to decide. So all right, so let's start with the complex vectors. Now, actually, let me also start recording here. So why are we talking about complex vectors, first of all? Well, I think you all know about the real vectors, right? I mean, from the physics course, we already know about for example, vector projection, how a specific vector can be projected into a specific direction, right? But complex vectors, you may be less familiar. The complex vectors are very common in electromagnetics because usually we actually, describe electric and magnetic fields with complex vectors. Okay, so let me just give you, and I'm not gonna spend a lot of time with this complex vectors, for the sake of looking at other concepts in electromagnetics. So, but I'm gonna summarize this with just one example, okay, which is I think sufficient for our purpose. So let's look at complex vectors. Okay, so I'm going to do this with an example. And like I said, let's, for example, consider a vector C. Okay, this is a complex vector. Okay, and it is given as the following: J x hat plus 1 plus J y hat plus 3 minus J4 z hat. Okay, so this is just a complex vector. So if you compare it with the real vectors, the only difference is that now the components of this vector are complex numbers. That's it. That's just what it makes it complex vector. Okay. And now I'm going to also define another vector d. Okay, and I'm going to look at the operations of these vectors basically with each other. So let's say the vector d is given as the following: 2 minus j3 x hat, this is the x component, and then j2 y hat, this is the y component, and then minus 2 z hat. So z component is, for example, here is real, but the other components are complex. So now let's look at, for example, different operations. Let's say we want to add these two vectors. Okay, so if we want to add these two vectors, for example, c plus d, we know from the real vectors is that if you have a c and d real vectors, you should be knowing how to add this two vectors and get the resultant vector, right? So in this case, it's the same essentially. So we basically add component by component, right? The x component with x component, y component with y component, and so on. And then if you do this, for example, if you add these two x components here together, so you will get 2 minus j2, 2 minus j2 x hat, and the y component will give you 1 plus j3, right? 1 plus j3 y hat, and then z component will give you this plus that will give you just 1 minus j4 z hat. Okay, so this is simple summation. And the subtraction is the same, so I don't even have to do it. You just subtract it. In fact, there's not much difference between those two operations. And what about the dot product, for example, okay? Or the inner product, C dot D. If I want to take the dot product of two complex vectors, again, you should be familiar with the real vectors, and the idea is the same. We just multiply instead of adding. Now we multiply these components component by component. So j multiplied with this, plus this is multiplied with this component, plus this is multiplied with that component. Okay, so if we do that, for example, if I multiply j with the 2 minus j 2 minus j3, it's going to give you the following: 3 plus j2, okay, and then if you multiply y components again respectively, you will get, now you should add this with minus 2 plus j2, and then now z components, multiplication of the z components will give you 5 minus j4. Okay, I'm sorry, not 5, sorry, plus j2, minus 6 plus, actually let me rewrite here, sorry, minus 6 plus j8. And this will give you, if you just calculate these or add these complex numbers, it's going to give you minus 5 plus j12. So the real part of this product is minus 5 and the imaginary part is 12. In fact, the dot product produces a scalar number, scalar complex number. Okay, so pay attention to that. So dot product, it's similar to the real vectors. Dot product will give you basically a scalar number. It's going to be actually the physical meaning of this is that, you know, basically in the real vector case, for example, is the projection of this d vector onto c vector, you know, the component, in other words, the component of d vector on c vector. But it is slightly different in the complex. So I don't want to go into detail at the moment about this one. But we will probably talk about that at some point in the future lectures. So the other, you know, important operation is the cross product. Okay, C cross D. Now, how do we do cross product? Well, it's again like similar to multiplication, right? Each element, for example, you multiply this element, the JX element with each of these three elements, and then add it together with the multiplication of the second element with the other ones, plus this multiplied with each of these, and you add all these things together. So it's the same idea. The only thing is that, of course, you have to be careful. For example, when you multiply this with this term with this term, there is an x cross x, because there's a cross product. X cross x will give you 0. X cross y will give you z hat, right? And you can, in fact, see this from this, you know, coordinate system. If this is, let's say, if this is x, this is y, this is z hat, x hat, y hat. Now you can see that x cross y will give you z hat, okay? And x cross z will give you minus y hat, okay? So you will basically do all these cross products, and at the end, you will arrive at this result, which you can do yourself as an exercise, and you should get this result. Minus 6 minus j15 y hat minus 7 plus j z hat. So this will be your cross product, and it's again a vector. In fact, in real vectors, this C cross D will give you a perpendicular vector, which is a vector which is perpendicular to both of these two vectors. But this is how you do it in the complex space, okay? So now here, I did not use a determinant, but there is another way of calculating this with the determinant, okay? So I'm gonna show you that too, because it's very useful actually. So how to do this cross product using determinant of a 3x3 matrix, okay? So let's look at this one. And for that, I'm gonna consider a slightly different example. So C cross D complex conjugate. Let's, for example, calculate this one. Now, what is D complex conjugate? Well, D complex conjugate is just a complex version or complex conjugate version of D vector. Okay, so let's first write that if you want. Let me actually write it maybe here. Okay, D complex conjugate, which is, you know, the complex conjugate of this vector, is basically 2 plus j3 x hat minus j2 y hat minus 2 z hat. So that's how you calculate the complex conjugate. Now, how do we calculate C cross D complex conjugate using a determinant of a 3x3 matrix? Okay, you could also use the same technique which we used here, but the other technique is the determinant, which is actually very useful in other calculations. So let's do this one. C cross D complex conjugate. You can write it this way. So first you write x hat, y hat, z hat, okay? Then you write the C vector here, j, 1 plus j, so that's the y component of the C vector, and the z component of the C vector is 3 minus j4, 3 minus j4. And then you write the D vector here as a, actually not D vector, but D complex conjugate. again as this row here, and it is given by this, so it's going to be 2 plus j3, and then minus j2 is this element, and then minus 2 is here. Okay, so you first construct this matrix. So this is just the coordinate system, unit vectors, and this is the first vector here, and this is the second vector. Vector C, vector D complex conjugate. Now from here, you need to take the determinant of this. So if you take the determinant of this matrix, then you should obtain the following. So from the determinant of this, okay, of this matrix, then you should obtain basically, now how do we do the determinant? So this is how you do it. So determinant is calculated like the following. In fact, this is, even though we use a square bracket here, the determinant should be usually given by a straight line, okay? So that's why I want to actually write it as a straight wire, which is different than your textbook. In that case, I can make this equal sign. That was the reason why I didn't want to put minus sign, put a equality sign here. But if you do it this way, then you can actually put a equality sign, because then this really means determinant. Okay. So so now if you do the determinant of this, now you will basically write x set, you will write x set, and then you will multiply minus 2 with 1 plus j, okay, and then minus j2 times this element here, minus j2 times 3 minus j4. This will be the x set element from this calculation. And then you have a y hat component, which will be, you will have a minus sign here because of this determinant calculation. And then you will have, so there is a parenthesis here, and then you will just cross y hat, row and this column here. Then you will have minus 2j minus 2 plus j3 multiplied with 3 minus j4. Okay, this is your y component, and note this minus sign here, and then plus z hat. Again, you cross this and that, this row and this column, and then you will have minus j2 multiplied with j, and then minus 2 plus j, 2 plus j3 multiplied with 1 plus j. Okay, so now if you just, it's just a bunch of calculations here. If you just calculate these, then the result will be the following. So you will obtain the following result. So x set component will be 6 plus j4, and then you have y hat component 18 plus j3, and then z hat component will be 3 minus j5. Okay, so this will be your C cross D complex conjugate. In fact, this specific cross product is very common in the power calculation, the power associated with the electromagnetic waves. So that's why actually we calculated this. And then I'm gonna finish with this example, D dot D complex conjugate. Okay, this is also another important, product which is very common in electromagnetics. In fact, this is related to the intensity or the power of the electromagnetic wave, and this is related to power flow. How much power propagates in what direction. So that's related to that, and we will look at this in more detail. And this is related to the power, the power contained in the electromagnetic wave. So so again, you can calculate this. D complex conjugate is given by this, and D is given by that. Again, you just by multiplying each component, and adding them together, you will get basically 13 plus 4 plus 4 is equal to 21. So that's the 21. All right, so that's it all about the complex vectors. Do you have any question? I noticed that there are a few comments about in the chat, but I would suggest you to interrupt and speak, because it's gonna be not very efficient through the chat, reading it and then answering it. And also sometimes I may miss those chat questions, because during the lecture it is hard to keep track of the chat box. Okay, so if you do you have any question about those chat questions, the things in the chat?
So when we're doing determinants and stuff,
Yeah.
are we supposed to do them by hand, or will we be able to use a calculator?
Well, if your calculator can handle symbolic, calculations as well, because sometimes this is numerical example, but sometimes you may also have symbolic, cross products as well. In those, in other words, those will be analytical calculations, and in those cases, I don't know if your calculator is capable of doing that. So, but it's a good idea to learn the general methodology of that. Okay, because you may encounter this issue with some problems which may not be necessarily solved by calculator. If it's a numerical, it's fine, you can do it. But please understand how this is calculated, though, even though you use it, a calculator. Any other questions? I mean, the reason why I wanted to talk about this is that in the past, I actually noticed that there were a lot of issues in the student papers about these basic concepts. So I was actually not talking about this in the past, but now I decided to include this also. So anyway, so now that's it about the complex vectors. Now I'm gonna talk about actual electromagnetics, and then you will see, why we covered these complex vectors, because in fact, electric and magnetic fields, which we would be looking at, are in fact related to, or most of the time they are expressed as complex vectors. So the next thing which I'm going to look at is about the Maxwell's equation. So let's remember the Maxwell's equations. Okay. So this is now electromagnetics, actually. This was just math, vector calculus. So now Maxwell's equations. All right, so in the Maxwell's equations, now we have actually these 4 equations, right? Curl E is equal to, del B by del T. So this says, basically, the electric field is related to rate of decrease of the magnetic field, magnetic flux density, actually. Okay, the electric field is generated if you look at a specific location in space. Okay, if you look at a specific location in space, it tells you that if there is a decrease in the rate of magnetic flux density, it must generate electric field at that location. And that electric field is related to this relation here with the curl operation. And I'm going to define this curl operation also, so you will know what it is. What kind of operation is that? Okay, so this is how the electric and magnetic field are related. In fact, B here is the magnetic flux density. It is related to the magnetic field through constitutive relations, which I'm going to show you as well. The other equation, Maxwell's equation, is curl H, and this is equal to J plus del D by del T. So that's there's a question here. That is here, if you are asking about this, this is the delta, actually nabla operator. So it's inverse delta or inverse, yeah, it's a triangle in that sense. It's a nabla operator. I'm going to define this in more detail later on, so you know what actually it does. Okay, it's a specific vector operator. Okay, curl H is given by this. And then we have also these equations. divergence B is equal to 0, and divergence D is equal to electric charge density. Okay, so these are called divergence. You know, if you have a dot product with this operator and the complex vector, or it can be a real vector too, actually. In this case, it's real. So this operation is called divergence. Okay, and these things are called curl. Now, what these equations are very interesting equations. So if you just pick a specific point, just the tip of this, pen, for example, at that point, if you look at that point, there is an electric field and magnetic field there, and this electric and magnetic field, they are actually related to each other through these four equations. It's amazing, actually. So this is true. We have a lot of stray electromagnetic fields around, and that actually obeys these equations. It's very, very interesting. So now I'm going to look at, if you, for example, consider just this equation, for example, it says that there is a relation between magnetic field at that location and the corresponding electric flux density and the current density if there is any current flowing at that point. Now here, of course, at the tip of this pen, there is no current flowing. So that's why J is equal to 0. However, there may be some, this quantity or electric flux density, which may be existing, and there is a relation between the corresponding magnetic field. And this magnetic field here, if it is changing in time, it will also produce electric field. Okay, and also divergence of that magnetic flux density, which is related to this H, that must be 0. And divergence of this D must be equal to the charge density, electric charge density. Okay, it all happens, at just here at this point. So let me also just briefly give you the units of this. For example, electric field here has a units of volt per meter, and then the magnetic field here is ampere per meter, and the magnetic flux here has the units of Weber per meter squared, Weber per meter squared, and then the current density, okay, that's the ampere per meter squared. And then the electric flux density has Coulomb per meter squared. And this is the electric charge density. It has the units of Coulomb per meter cube. Okay, so these are the just those units. And like I said, this B and D are actually related to E and H. And let me also add this. These are not the Maxwell's equations, but they are called constitutive relations, which let me also just add it here just for completeness. In fact, B is equal to mu times H. That's how the magnetic flux density is related to magnetic field. And mu is called magnetic permeability of the material in which this electromagnetic field is residing. Magnetic permeability. And similarly, for the electric flux density, it is equal to epsilon times E. Okay, so that's this electric field, and this is called electric permittivity. Electric permittivity. Okay, so this is the epsilon electric permittivity, and again, this is related to this electric flux density through this equation. So everything here, E and H, they are related to each other. Okay, so now this J and rho V here, they are actually usually called sources, because these are actually the origin of any electromagnetic field. If there is no current density in the environment, or there is no charge density, then it is not possible to have any electromagnetic field. Okay, so you need to be careful about this. If there is no electric current density or charge, then there is no electromagnetic field. You have to be aware of this. So there is always, you have antennas on your cell phones, and there are a lot of electromagnetic sources, right? The router at your home, and these transmission lines around. So they all produce electromagnetic fields, and they are related to this J and rho V. Okay, so now the next thing which I want to now explain is, what, okay, that's good, but what about this curl and the divergence operators? How do we define them? Okay, because if you don't know how to define them, then you cannot calculate this, obviously. So that's why now next I'm going to introduce these operators so we better understand the Maxwell's equations. So this operator, okay, is called nabla operator. It's a vector operator, and it's, it is called nabla. Okay, so let's understand this operator. Now, this operator is actually described mathematically as the following. So it is x hat del by del x plus y hat del by del y plus z hat del by del z. Okay, so this is how the nabla operator is defined. It's the same. It's very similar to a vector, ordinary vector, except that it's not. It's actually an operator. It's a vector operator because each component actually acts on a vector, and you evaluate that operation through this derivatives here. So that's why it's an operator. It operates on a vector actually. Okay. So now, so let's also define, for example, an arbitrary vector, okay? Let's define just an arbitrary vector A. If this arbitrary vector is defined as the following, let's say it has an x component, and this x component is a function of both all of these x, y, and z variables. Okay, this is the x component of that vector, and then it has a y component, and I'm gonna again write it in this form. So y component also depends all the coordinates, and then there is a z component which may also depend all these components, all these x, y, z coordinates. Okay, now you have this arbitrary vector. Each component is a function of x, y, and z. Okay, and this may be a complex or not. Okay. This a, y, a, x, a, y, a, z, they can be a complex or they can be real. Okay, so this operator can act all kinds of operators, complex or real. Now, how would you calculate, for example, curl A? Okay, in fact, up to now, you know this. Even though you may have not noticed it, you know how to do this actually, because you have the mathematical information. Which has already been provided in a few, in the last few minutes. So it's very simple. This is the operator, and this is vector A. You just go to this, determinant calculation. You write x, y, you write x, y, z here. Then you write the operator, curl operator, or the nabla operator in the second line, which will be actually components of which are del by del x, del by del y, del by del z. And then the third line will be just the a vector. So in fact, this will be just written like this. So determinant, let me write here. So determinant will be x hat, y hat, z hat, and then you will have this operator, vector operator. You will write each components of that. So del by del x, del by del y, and del by del z. And then you need to write a in this line, which is ax, ay, and az. So if you just calculate the determinant of this, it's going to give you the following. I'm going to finish with this. Del by del az by del y minus del ay by del z. Okay, this is the x component of this operator, or this operation. And then y hat component will be del ax by del z minus del az divided by del x. Okay, and then plus z hat component, which is del ay by del x minus del ax divided by del y. Okay, so this is your z component. It's essentially determinant, like we calculated here, except that now you don't have a vector. You have a vector operator. You don't have a complex, simple complex, or ordinary complex vector. It is actually a vector operator. So be careful about it. But the idea is the same. Determinant, you will just use the determinant in the same way. So I'm going to continue in the next lecture about, also divergence, how to calculate divergence and their physical meaning and how they are related to electromagnetic fields. So with that, I'm going to stop here unless you have any questions.
Should the coefficient in front of y be negative like in the first problem, or is it just positive?
It's already being accounted here. It should be already accounted here. Okay,
Oh, okay.
So there's a minus sign, so it's just shifted.
Gotcha. I see that now.
Yeah.
Thank you.
Mm-hmm. Any other question?
Will this stuff be in the book, like the descriptions of the variables and about how they relate to, like, what it is? Does that make sense? Like the definitions of the variables.
I'm sorry, say it again.
Will these definitions be in the book? Because like a lot of what you said, obviously you didn't write down. So I'm just curious.
Yeah, they are. You can find this in the book, except that I think it doesn't directly explain this in terms of determinant. Yeah.
Okay.
But it is a very instructive to actually relate to determinant, because otherwise, if the book just, I think, directly writes this expression, so it doesn't tell how it's calculated. So I think if you use the determinant, it would actually make more sense.
Right. Will you explain again how the y hat doesn't have the negative?
Yeah, because if you look at this y hat component here, all you need to do is just cross this column and this row. Then it's going to be minus y hat, and then del az by del x minus del ax by del z. But this is just opposite. You need to actually, if you reverse this, then there will be a minus sign here.
Okay, thanks.
Okay. I mean, I follow the book, textbook, but there are some, sometimes there is a, I add more explanation, so to make the book more accessible. So there might be some slight things which you may not find in the book, but it is pretty much aligned with the book, though. Okay. All right. Any other questions? All right. So I'm going to stop here, and then I'll see you on Wednesday. Have a good rest of the day.